Hey guys, so as you can see, hopefully you noticed I'm not at school today, but that doesn't mean we get out of work because we have one more thing we need to learn before we go ahead and do our final, which is coming up in a little over 2 weeks. So we have to learn one more thing as well as remember everything else we've done. That way we can be prepared for our final that's coming up real soon. So what we've been working on right before break and what we took our quiz on right before break was ionic bonds. An ionic bond, remember, is when the metal transfers its electrons to the nonmetal, giving them a more stable combination. So like sodium and chlorine, when sodium gives its electrons to chlorine, sodium becomes more stable. That's why it doesn't explode. Chlorine becomes more stable. That's why it's not a toxic gas. That's why when we combine them, we get something like table salt where they combine, they're both stable, they're both boring now. Okay. Instead of really exciting, really toxic, they both become really stable, really boring, chilled out. So when we look at those things, that's great. When we talk about covalent bonds, we're talking about something a little bit different. Ionic bonds have that metal and the nonmetal, the left side and the right side of the periodic table. Now we're talking about covalent bonds. Covalent bonds is all over here on the right side of the periodic table. They're all going to be nonmetals. So we're going to have two or even sometimes more nonmetals and only nonmetals. Okay, so things like carbon, nitrogen, fluorine, chlorine, bromine, oxygen. Those things are all nonmetals because they have more valence electrons and they don't want to give them away. So that's the problem we have with covalent bonds is they don't want to give away their electrons. Metals always try to give them away because they don't want them. If they're happier, they're more stable without them. Nonmetals are always trying to take electrons because they're stable or happy with more electrons. They want to hold on to all of them. But if we have two nonmetals, they're trying to combine. And when that happens, they're going to end up sharing their electrons instead. So they share their electrons to form these covalent bonds. So again, nonmetal and metal. When we have a metal and nonmetal, it's an ionic bond because the electrons transfer from the metal to the nonmetal. Covalent bonds, they share their electrons to create a covalent bond. So two nonmetals share electrons. So we're talking about covalent bonds on this worksheet that we're going to be looking at today. And so in covalent bonds, again, one more time, they share their electrons between two nonmetals, okay? Only the right side of the periodic table. The electrons are shared in three different types of bonds. We have single bonds, double bonds, and triple bonds. Single bonds means that we have one electron from each of our atoms that are going to be shared. Okay? So there's a total of two electrons in the bond, but only one from each atom that are sharing. In a double bond, we have two electrons from each atom that are shared for a total of four electrons. And for a triple bond, we have three electrons from each atom that are going to be shared, creating a triple bond. So a total of six electrons. Okay? It all depends on the number of electrons that are left unpaired when we are looking at the Lewis dot structure. So before we do anything else, let's refresh. Okay, the Lewis dot structure, I'm going to do it up in the corner. We start with an element, any element. I'm going to use X as an example, just because X in math class is our variable of choice. Okay, so if we remember, we start with one valence electron. We go 2, 3, 4. Okay, so we do one on each of our four sides first. Then we go back and we do 5, 6, 7, and 8. Okay, so then we go to a second one on each side. Okay, so that's going to be super important when we do our covalent bonds because it shows us where the extra electrons need to be shared from. Okay, so if we take a look at nitrogen as our example, nitrogen has 5 valence electrons and it has 3 that are unpaired. This is called a lone pair because it's a lone, it's a pair, we don't touch it. We're never going to use that as part of our covalent bond. It gets to stay there. It always has to be there. The other ones, if we look, we have 1, 2, 3 electrons that are not paired up. They're not happy because they're all by themselves. All our electrons want to be in that pair, and because these two aren't, it wants to create a bond some way or another. In ionic bonds, when we gain electrons, that's why we gain electrons for those empty spaces. But in covalent bonds, those tell us the places that our electrons are going to be shared for. So it tells us that we have up to 3 bonds that we need to create because there's 3 unpaired electrons. If we do one more together before I let you guys work on the rest, okay? If we look at oxygen, oxygen is the letter O. And if we look at our periodic table, we look for the number of valence electrons. So we count the tall columns, so starting with column 1 all the way in the left with hydrogen. We go 1, 2, we skip that middle section, 3, 4, 5, 6, and we get to oxygen. It's in the 6th tall column. So we go 1, 2, 3, 4, 5, 6. Okay, so that if we count those, we have 2 sets of lone pairs. They're already paired up. They do not want to interact with other elements. They're going to hang out by themselves. These other electrons over here, these 1, 2, those 2 electrons are unpaired. That means they want to bond with something else, or they want to have 2 other electrons either shared or given to them. So that means oxygen is willing to have 2 bonds because it has 2 open spaces. Right? So you have 4 more just like that to work on. We're actually going to keep going down, and we're going to go ahead and do one of the practice problems down below real quick. Okay, so we're going to scroll down to page 2. On page 2, it says draw the Lewis dot structure and circle the electrons that are going to bond. So we're going to go to O2, which is just oxygen. Oxygen is something we call a diatomic. When it's by itself, it needs to be bonded with something else. Same with chlorine. You're going to see that there are 7 of them in total. And I'll write them up here just so we remember. Diatomic. The diatomics are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Okay? Not super important right now, but it's going to come up later when we talk about reactions, what diatomics are and how to write them. Okay, so it's going to be super important later that we know these. So if you guys look, if we ignore hydrogen, the rest of them over on the side make a little 7, which is a good reminder to tell us that there are 7 diatomics that we might have to look out for. When they're in a bond with something else, like if we look at PCl3, phosphorus and chlorine, there's more than 2 chlorines. It can have 1 chlorine or 3 or 4 or even 5. It only needs to have 3, or only needs to have 2 when it's by itself. So like O2 is by itself. So when we draw this bond, we're going to draw O with its 1, 2, 3, 4, 5, 6 valence electrons. And we have to do it 2 times because it says O2. I'm going to draw it right underneath. 1, 2, 3, 4, 5, 6. Okay. And so again, if we remember, our oxygen wants 2 bonds each. So what's going to happen is our oxygens are going to bond by sharing their unpaired electrons. So we're going to circle those 2 to show that those unpaired electrons are being shared. And when that happens, we redraw it with a line for every pair of electrons we're sharing. So one line means each oxygen is sharing 1 electron for a total of 2, but we have 1, 2 sets. So we need to have a second line to show that we're sharing 2 sets of electrons each. Okay. But last thing we have to do is add these extra lone pairs back on. So we go 1, 2, 3, 4. 1, 2, 3, 4. So if we were to count our electrons, we have 1, 2, 3, 4, 5, 6, 7, 8 from our bond and our four our lone pairs. Okay. And then the same thing on the other oxygen has 8 again. So we don't need to write those out, but we can count those 8 electrons. So that way we can see that those electrons are actually there. Okay, this is just our final answer. Okay, so you have 2 more of those to practice. Okay, and then we have one more thing we need to do. Okay, just like in ionic bonds, we need to take those names and come up with formulas. These ones are a little bit different because these ones actually might be easier once we get the hang of it and once we know what these prefixes are. Okay, and when I say we have to know these prefixes, we're going to have to know them because I'm not going to give them to you on a test. So I want to help remember some of these ones. Okay, we talked about last week, well, not last week, the week before break, we talked about mono because we talked about polyatomics, meaning multiple, and we talked about mono. Do you guys remember what that number was? Hopefully in your head at least, or maybe even out loud, you guys said that mono meant 1. So mono is the prefix for 1. So that tells us we have 1 of that atom. Okay. Up above, we talked about diatomics. What do all of those elements have in common? How many of them do you have when they're alone? Hopefully you realize that di means 2. So the prefix di means 2. Okay. If we're thinking about tri, we're thinking about maybe triangles or tricycles, which all have the same thing in common. That prefix tells us there's 3 of something, right? A triangle has 3 points, a tricycle has 3 wheels. Tri means 3. Tetra. Tetra is probably the hardest one to remember. If you guys know the game Tetris, I know that it might be outdated at this point. It might just be something that I played as a kid, but Tetris, all of the boxes for Tetris have 4 little cubes that make up their box. And so Tetra is like Tetris, it means 4. So Tetra means 4. Penta, think of like a pentagon, like 5 sides, or like the pentagon, like the building has 5 sides. Penta means 5. Hexa, like a hexagon. Hexagons are 6 sides. Hepta, you probably don't talk about heptagons a lot, but heptagons is a 7-sided thing. Octa, I know we've talked about octa before because we talked about the octet rule, which was the number of valence electrons, the goal amount for our atoms. We've talked about octopus, and we talked about octagons when we were thinking about the octet rule because I talked to a lot of you about that. Octa means 8. Nana, you probably don't talk about nonagons a lot either, but nana means 9. And deca, think about like a decade. A decade is 10 years. You can also think about a decagon if you think that way. Deca just means 10. Okay? And so when we talk about these prefixes, we're going to see that these names have these prefixes in them. So if we look at the first one says nitrogen and says there's no prefix, okay? Just kind of like ionic bonds when we talked about not putting the 1 in front of it if it had a 1. If there's no prefix for the first element only, it just means that there's 1 of them. So our first element's nitrogen. So the symbol for nitrogen is just N. Right? And since there's no prefix in front, we're going to have just 1 of them. Okay. The second element is chloride. And remember, the ending changes a little bit, just like in ionic bonds. We changed the ending from our element on the periodic table to help us out, right? To tell us that it was in a compound. So the second element is chloride. Chloride kind of sounds like, hopefully in your heads at least, you said it was chlorine. And then this prefix in front of chlorine is tri, and tri, if we look up above, is 3. Okay, so if we put this together for our formula, we have N, and we only have 1 of them, so we can put the 1, but we don't have to. And then we have chloride, which is chlorine, and we have 3 of them, so we're going to put the 3. If you guys have any questions, please let me know. Otherwise, I'll be back tomorrow to refresh and go over this again. Have a good rest of your day.